Hi, welcome to iEducator. This is Teacher Jeff. I'm an educator and an engineer by profession. And today we will discuss Chapter 2. And Chapter 2 is all about problem solving tools. And in today's lesson, there are two key areas that I'm going to be highlighting. First, we have the exploratory tools, and second, we have the recording tools. And so for that matter, let us discuss first the first key area of our presentation, which is rather the exploratory tools. Now here, you need to remember that a good methods engineering program will actually follow an orderly process, meaning to say it follows certain step-by-step process or procedure, starting from the selection of the project and ending with the implementation of the project. The first and perhaps most crucial step, whether designing a new work center or improving an existing operation, is that would be the identification of the problem in a clear and logical form, of course. Just as the machinist uses tools such as micrometers and calipers to facilitate performance, so the methods engineer uses appropriate tools to do a better job in shorter time. A variety of such problem-solving tools are available, and each tool has specific applications. Now, just a brief recap. Remember that in Chapter 1, we discussed about the principal steps in a methods engineering program or methods analysis, right? And we learned that the principal steps in a methods engineering program or a methods analysis, first we have selecting the problem. Second, getting and presenting the data. Third, we have analyzing the data. Fourth, developing ideal method. Fifth, we have presenting and installing the method. Sixth, developing job analysis, followed by establishing time standards, and lasted by following up. Now, the first 5 exploratory tools are primarily used in the first step of methods analysis, which is selecting the problem. Now, these exploratory tools are the following. First, we have Pareto Analysis. This is also known as Pareto Diagram, Pareto Chart, or 80-20% rule. This is named as Pareto Analysis or Pareto Diagram because it was Vilfredo Pareto, an Italian economist, who discovered this exploratory tool. And another exploratory tool that would be Fishbone Diagram, also known as Ishikawa Diagram or Cause and Effect Analysis. And also we have Gantt Chart. We also have program or project evaluation and review technique or PERT, and also known as the network diagram or the critical path method. And finally, we also have job worksite analysis guide. Take note that Pareto analysis and fishbone diagrams evolved from Japanese quality circles of the early 1960s and were quite successful in improving quality and reducing costs in their manufacturing processes. On the other hand, Gantt chart and PERT chart emerged during the 1940s in response to a need for a better project planning and control of complex military projects. They can also be very useful in identifying problems in an industrial setting. Now, the first 4 exploratory tools are most typically used in the analyst's office. And the 5th tool, which is Job or Worksite Analysis Guide, it helps identify problems within a particular area, department, or work site, and is best developed as part of a physical walkthrough and on-site observations. Now, the guide provides a subjective identification of key worker, task, environmental, and administrative factors that may cause potential problems. It also indicates rather appropriate tools for further, more quantitative evaluations. Use of the job or worksite analysis guide should be a necessary first step before extensive quantitative data are collected on the present method. And typically, project selection is based on three considerations. First, we have economic consideration, followed by technical consideration, and lasted by human consideration. Now, why is it that project selection is based on these three considerations? Now, if we say economic considerations, this may involve new products for which standards have not been implemented. In other words, it can also involve existing products that have a high cost of manufacturing. Problems could be large amounts of scrap or rework, excessive material handling in terms of either cost or distance, or simply bottleneck operations. On the other hand, technical considerations may include processing techniques that need to be improved, quality control problems due to method, or product performance problems compared to the competition. And for human considerations may involve highly repetitive jobs leading to work-related musculoskeletal injuries or MSDs injuries. Also, we have high accident rate jobs, excessively fatiguing jobs, or even jobs out which workers constantly complain. As you can see, the next five tools are used to record the present method, and they comprise the second step of methods analysis, which is getting and presenting the data. Now, these tools are called recording and analysis tools, and these tools are the following. First, we have the operation process chart. Second, we have flow process chart. Next, flow diagram, followed by worker and machine process chart, and lasted by gang process chart. Now, remember, pertinent factual information such as the production quantity, delivery schedules, operational times, facilities, machine capacities, special materials, and special tools may have an important bearing on the solution of the problem, and such information needs to be recorded. Now, in order for us to better understand the exploratory tools, let us discuss them one by one, starting with Pareto analysis. So what is meant by Pareto analysis then? Now, Pareto analysis is also known as Pareto principle, 80-20% rule, the law of the vital few, and the principle of factor sparsity. Now, in Pareto analysis, items of interest are actually identified and then measured on a common scale, and then are ordered in descending order as a cumulative distribution. And second, it is developed by the late Italian economist by the name of Vilfredo Pareto, who studied the concentration of wealth. And based on his study, he observed that only 20% of people held the majority of wealth. And this principle illustrates that 80% of effects arise from 20% of the causes, or in layman's terms, 20% of your actions or activities will account for 80% of your results or outcomes. Now, typically, 20% of the ranked items account for 80% or more of the total activity. And consequently, the technique is sometimes called the 80-20 rule. For example, 80% of the total inventory is found in only 20% of the inventory items, or 20% of the jobs account for approximately 80% of the accidents, or 20% of the jobs account for 80% of the workers' compensation cost. Now, Dr. Joseph Juran was the first to point out that what Pareto and others had observed was a universal principle. If I say universal principle, what I mean about that is that one that applied in an astounding variety of situations, not just economic activity, and appeared to hold without exception in problems of quality. So in the early 1950s, Juran noted that universal phenomenon that he has called the Pareto principle, that in any group of factors contributing to a common effect, a relative few account for the bulk of the effect. So Juran has also coined the terms vital few and useful many, or trivial many, to refer to those few contributions which account for the bulk of the effect, and to those many others which account for a smaller proportion of the effect. And conceptually speaking, what the methods analysts usually concentrate on is that they concentrate on the greatest effort on the few jobs that produce most of the problems. And in many cases, the Pareto distribution can be transformed to a straight line using a log normal transformation, from which further quantitative analysis can be performed. Now, as you can see, these are examples of Pareto analysis. So if you can notice, your X in the first example, if you can notice, the X-axis refers to the causes, okay? And for the y-axis, this refers to the count of errors. And as you can see, you have there a line, or 80% line, meaning to say that is the cutoff line, okay? And you also have the trivial many in the right side, and you also have the vital few. Now, what do we mean by vital few and trivial many? Now, if you can notice, in a Pareto analysis, this is what we call somewhat like a prioritization. So if you conduct a certain study in regards to defects, for example, or errors, based on our example on number 1, as you can see, the top 3 errors that we have are broken links. We also have spelling errors, and we also have missing title tag. And these 3 errors are under our vital few, okay? And the rest of the errors, we call them the trivial many, meaning to say they have contributed to the causes of the errors, but it doesn't have that much effect compared to these 3. So in other words, we need to draw our attention, our full focus on the top 3 reasons for the errors, which are the broken links, spelling errors, and the missing title tag. On the other hand, on the right side corner of the presentation, you have there another example of a Pareto chart, and this example is the types of medication error. Now, if you can notice, same with the first example, the first axis refers to the different errors, and the y-axis refers to the frequency or the count of the particular errors, okay? And as you can notice, it is highlighted there, your trivial many and your vital few. In your vital few, there are top 4 errors included, in which you will be drawing your attention and making sure that your full focus should be there. And the top 4 error that we should be solving, we should be sorting out, that would be first, dose missed. We also have wrong time, wrong drug, and overdose. And the rest are considered as trivial many already. All right, so this is an example of a Pareto analysis. This is just an overview of what a Pareto analysis is and how it looks like. But don't you worry, this will be discussed further in a separate video. Okay, and the next exploratory tool that we have, that would be called Fishbone Diagram. And as mentioned earlier, Fishbone Diagram is also known as Ishikawa Diagram and Cause and Effect Diagram. Now, as you can see, it is developed by Karo Ishikawa in the early 1950s while he was working on a quality control project for Kawasaki Steel Company. And this method consists of defining an occurrence of a typically undesirable event or problem. That is the effect, or which refers to our fish head. And then identifying contributing factors, that is the causes, as fish bones attached to a backbone and the fish head. And the principal causes are typically subdivided into 6 major categories. First, we have man, machines, methods, materials, measurement, and mother nature. Now, each of which is further divided or subdivided into subcauses. Now, the process is actually continued until all possible causes are listed. And take note, a good diagram will have several levels of bones and will provide a very good overview of a problem and its contributing factors. Now, the factors are then critically analyzed in terms of their probable contribution to the overall problem. This process will also tend to identify potential solution. Now, in order for us to better understand what fishbone diagram is and how it looks like, let me provide you an example. As you can see, this is an example of a fishbone diagram. Now, this is considered, or this is called as a fishbone diagram because it's just like a skeleton of a fish, right? You have there a fish head and you have there different spines of the fish. Now, take note that in our definition, our fish head refers to the effects, okay? And our different 6 spines refer to the causes. Now, as you can notice in our fishbone diagram, in each spine, you have their lines written horizontally, correct? Can you see that? Okay, now those lines that are written horizontally, this refer to the major causes. And the other lines which are written diagonally, these refer to our two probable causes or underlying causes. Now, as you can see in our fish head, our effect is bad burgers, right? Now, just imagine you're visiting a fast food restaurant. Okay, let's just say McDonald's. Okay, now in McDonald's, you went to counter, you ordered a burger, and when you received your burger and you ate it, there's something wrong with the taste. So you consider that as a bad burger. Now, as a customer, you wanted to know why. You wanted to know the reasons, the underlying causes, and the major causes why the taste of the burger is bad. Now, since you want to know the reasons why, you need to make use of the different spines, okay? You have their manpower, the measurement, mother nature, machines, methods, and materials. Now, in terms of manpower, what might be the reason, or what can be one reason that causes a bad burger? Now, as you can see there, you have their mishandling, okay? So maybe mishandling contributed to the taste of the burger, okay? Because the personnel there are not following GMP or good manufacturing practices, or we may have HACCP or hazard analysis and critical control points. So that's very important, GMP and HACCP, if our nature of business is a food business. Okay, so there is a mishandling. So why you will ask yourself, why mishandling? Because unhygienic storage. So meaning to say, they do not clean properly their utensils, maybe. And also you have insufficient training on how to cook and store. Meaning to say, those personnel working there in that certain store were only oriented or trained the moment they were hired by the company, but there's no uh, another relevant seminars or trainings. Okay, so there are no further trainings at all, so there is an insufficiency of the training on the part of the personnel. Okay, what about materials? Now we write there raw materials. So why raw materials? The raw materials are not fresh. Okay. Another, uh, under raw materials, you have there not as per prescribed quality. Okay. So meaning to say, if the raw material itself is not fresh and is not as per prescribed by the quality, then the quality control officer should be responsible to that, if that makes sense, correct? Because that is their main job. That is their duty, to make sure that the raw materials should be fresh and within the prescribed quality or standard of the company, and so on and so forth. Okay, so that's how you create fishbone diagram. But don't you worry, this will be further discussed in a separate video. This is only for the presentation purposes. And the next exploratory tool that we have is what we call Gantt chart. If it's a Gantt chart, it is a type of bar chart that illustrates a project schedule named after its inventor, Henry Gantt, between 1861 to 1919, who designed such a chart around the years 1910 to 1915. Modern Gantt charts also show the dependency relationships between activities and the current schedule status. And take note that the Gantt chart was probably the first project planning and control technique to emerge during the 1940s in response to the need to manage complex defense projects and systems better. In other words, a Gantt chart simply shows the anticipated completion times for various project activities as bars plotted against time on the horizontal axis, and actual completion times are shown by shading the bars appropriately. Now, if a vertical line is drawn through a given date, you can easily determine which project components are ahead of a behind schedule. Now, as you can see, this is an example of a Gantt chart. So you have there, this is figure 2.3, and you have there 2.3a, which is the first picture or first example, and you have there figure 2.3b, which is the second example. Now, for example, as you can see in figure 2.3a, by the end of the third month, okay, take note of that. By the end of third month, mock-up work is behind schedule, right? A Gantt chart forces the project planner to develop a plan ahead of time and provides a quick snapshot of the progress of the project at any given time. But unfortunately, it does not always completely describe the interaction between different project activities, and more analytic techniques such as PERT charts are required for that purpose. Now, the Gantt chart can also be utilized for sequencing machine activity on the plan for, meaning the machine-based chart can include repair or maintenance activity by crossing out that time period in which the planned downtime will occur. On the other hand, for figure 2.3b, in the job shop example, in the middle of the month, lathe work is behind schedule, right? While production on the punch press is ahead of schedule. Okay, so this is an example of Gantt chart. This is a chart for planning and scheduling and making sure that you are able to meet your schedules on the desired deadlines. And the next exploratory tool that we will be discussing, that would be the PERT charting. Again, like I said earlier, PERT stands for Program or Project Evaluation and Review Technique. And it is also referred to as your network diagram or critical path method, or the CPM. And PERT chart is a planning and control tool that graphically portrays the optimum way to attain some predetermined objective, generally in terms of time. If you may know, this technique was actually employed by the US military in the design of their processes as the development of the Polaris missile and the operation of control systems in nuclear-powered submarines. Now here, in this period, methods analysts usually use PERT charting to improve scheduling through cost reduction or customer satisfaction. Now, in using PERT for scheduling, take note that analysts generally provide 2 or 3 time estimates for each activity. For example, if 3 time estimates are used, they are based on the following questions. First, how much time is required to complete a specific activity if everything works out ideally? Now, this refers to optimistic estimate. And second, under average conditions, what would be the most likely duration of this activity? And third, what is the time required to complete this activity if almost everything goes wrong? Now, this refers to pessimistic estimate. Now, with these estimates, the analyst can actually develop a probability distribution of the time required to perform the activity. And take note, on a PERT chart, events represented by nodes are positions in time that show the start and completion of a particular operation or group of operations. And each operation or group of operations in a department as an activity and is called an arc. Again, if we say arc, this refers to activity. And each arc has an attached number representing that time, may it be expressed in terms of days, weeks, or months needed to complete such activity. And these activities that utilize no time or cost yet are necessary to maintain a correct sequence are called dummy activities and are shown as dotted lines. Again, if we say dummy activities in a network diagram, dummy activities are represented by dotted line, okay? When we say dotted line, these are broken lines. And these dummy activities as well don't have what we call duration, okay? So take note about that. Now, in order for us to better understand a PERT charting and how it looks like, let me give you an example. Okay, now this is an example of a network diagram. As you can see, in activity H in figure 2.4, this is an example of a dummy activity as it is represented by dotted lines, as you can see in the one encircled with red, and that this activity utilizes no time or cost, yet is necessary to maintain a correct sequence. Like I said earlier, for the dummy activities, they do not have what we call duration. And dummy activities as well are typically used to indicate precedence or dependencies, because under the rules, no two activities can be identified by some nodes. That is, each activity has a unique set of nodes. As you can see in our sample network diagram, these numbered circles refer to nodes. So in this case, you have their nodes 1, 2, 3, 4, up until node 12, okay? So that means to say that our starting node is node number 1 and our ending node is node number 12. But don't you worry, this will be discussed further in a separate video. This is only given for presentation purposes. And the last exploratory tool that we have, that would be job or worksite analysis guide. Now, like I said earlier, if it's a job or worksite analysis guide, this identifies problems within a particular area, department, or worksite. So before collecting quantitative data, we need to make sure that the analyst first walks through the area and observes the worker, the task, the workplace, and the surrounding working environment. And in addition, the analyst also needs to identify any administrative factors that may affect the worker's behavior or performance. And all these factors provide an overall perspective of the situation and help guide the analyst in using other, more quantitative tools for collecting and analyzing the data. Now, this is an example of a job worksite analysis guide. And as you can see in figure 2.5, it shows the application of the job or worksite analysis guide to a hot-end operation in a television manufacturing facility. Now, key concerns include the lifting of heavy loads, heat stress, and noise exposure. Okay, so what you do here is generally you analyze the job, and while analyzing the job, you also need to determine if this job is hazardous to the workers themselves, and if it is, then what can you do to improve and to reduce these hazards, or even to eradicate these hazards, okay? So the next key area that we're gonna be discussing right now, that would be the recording and analysis tools. And we will discuss all the recording and analysis tools, starting with operation process chart. Now, what is meant by operation process chart? If we say operation process chart, it shows the chronological sequence of all operations, inspections, time allowances, and materials used in a manufacturing or business process, from the arrival of raw material to the packaging of the finished product. Now, this chart actually depicts the entrance of all components and sub-assemblies to the main assembly. Just as a blueprint displays such design details as fits, tolerances, and specifications, the operation process chart gives manufacturing and business details at a glance. Now, we have to take note that if we discuss operation process chart, we have to remember these two symbols. The two symbols that we need to always remember in constructing the operation process chart, that would be a small circle and a small square. Now, a small circle denotes an operation, and a small square denotes an inspection. So for the small circle, An operation takes place when a part being studied is intentionally transformed, or when it is being studied or planned prior to productive work being performed on it. On the other hand, for a small square, an inspection takes place when the part is being examined to determine its conformity to a standard. So take note that some analysts prefer to outline only the operations, calling the result an outline process chart. Now, before beginning the actual construction of the operation process chart, analysts identify the chart with the following information. First, you have there a title, and in this case, the title should be Operation Process Chart, and other information that we can be found and other information that can be found in such chart would be the part number, the drawing number, process description, present and proposed method, the date as to when the study was conducted, the name of the person doing the charting as well, or the name of the analysts doing the job or doing the analysis job. And third, additional information may include such items as the chart number, the plant or the name of the plant where you conducted your study, the building, and also the specific department. Now, as you can see, this is figure 2.6. And as you can see in figure 2.6, vertical lines indicate the general flow of the process as work is accomplished, while horizontal line feeding into the vertical flow lines indicate material either purchased or worked on during the process. Now, parts are shown as entering a vertical line for assembly or leaving a vertical line for disassembly. Now, materials are disassembled or extracted are represented by horizontal material lines drawn to the right of the vertical flow line, while assembly materials are shown as horizontal lines drawn to the left of the vertical flow line. Now, in general, the operation process chart is actually constructed such that vertical flow lines and horizontal material lines do not cross. In other words, if it becomes necessary to cross a vertical and horizontal line, we should need to use conventional practice to show that no juncture occurs. That is, draw a small semicircle in the horizontal line at the point where the vertical line crosses, as shown in figure 2.6. As you can see, this is figure 2.7, and this is an example of an operation process chart. Again, in constructing an operation process chart, the two symbols that we're going to be using, that would be the small circle and the small square. And take note that for small circle, this denotes operation. And for the small square, this denotes inspection. So in your study, so if you're studying an operation, employing an operation process chart, if the operator under observance is doing something on that particular product, then that is operation. But if that certain operator inspects the quality or the standard of that particular product, then you will be using square. Okay, so the sample completed operation process chart helps the analyst visualize the present method with all its details so that new and better procedures may be devised. Now, it shows analysts what effect a change on a given operation will have on the preceding and subsequent operations. It is not unusual to realize a 30% reduction in the performance time by utilizing the principles of operations analysis. in conjunction with the operation process chart, which inevitably suggests possibilities for improvement. And also, since each step is shown in its proper chronological sequence, the chart in itself is an ideal plant layout, meaning, consequently, methods analysts find this tool extremely helpful in developing new layouts and improving existing ones. Now, aside from operation process chart, we also have what we call flow process chart. Now, if we say flow process chart, it is a symbolic representation that illustrates the sequence of activities within a process. Why is it called symbolic representation? Because in constructing a flow process chart, we will be using 5 symbols. We will be able to know what these symbols are in the following section. And also, a flow process chart is used to record and analyze the activities that make up a process to determine which activity adds value and which do not. And take note, activities can be any operation, inspection, storage, transportation, and delay actions that are carried out by an individual person, a team, a machine, a computer system, or a combination of all. Now, in general, the flow process chart contains considerably greater detail than the operation process chart. Consequently, it is not usually applied to the entire assemblies, but rather for each component of an assembly. The flow process chart is especially valuable in recording non-production hidden costs, such as distances traveled by the operators, delays, it may be delay in terms of the operator or the machine or the material, and temporary storages as well. Now, once these non-production periods are being highlighted, analysts can then take steps to minimize them and hence their cost. And in addition to recording operations and inspections, flow process charts show all the moves and storage delays encountered by an item as it goes through the plant. Now, flow process charts, therefore, need several symbols in addition to the operation and inspection symbols, which are only used in the operation process chart. So what are the symbols used in the process flow chart then? Well, the symbols that are usually used in constructing a flow process chart, that would be circle. Circle represents operation. So example of operation we have, assuming that the operator is drilling a hole in a metal or drilling a hole in metal. Also, we have serving a customer in a contact center. Okay, these are all operations. So if it's an operation, the symbol we will be using is circle. Another symbol that we will be using in constructing a flow process chart, that would be square, and square represents inspection. So examples of inspection, assuming that the operator is checking the material or the product for defects, and also if the operator is measuring the dimensions of a product, that can be considered as an inspection. Another, we have if that certain operator is counting received products, okay? Because if you are counting, meaning to say, you make sure that the count is correct, right? So you are inspecting. And also if the operator is getting feedback from a customer as well. Now, the next symbol that we will be using in constructing a flow process chart, that would be the symbol inverted triangle, or an equilateral triangle standing on its vertex, which represents storage. And storage is used in storing of something until later time, meaning it usually occurs when a part is held and protected against unauthorized removal. Now, examples of storage, that would be storing of finished goods in a warehouse or storing of supplies received in a storeroom as inventory. Now, the next symbol that we have, the symbol inverted arrow, which represents transportation. Now, transportation is used in the movement of people, materials, or other items between locations, or it is used in moving an object from one place to another, except when the movement takes place during the normal course of an operation or inspection. So examples of transportation, that would be a forklift moving pallets from a warehouse into a loading bay. Also, a customer walking from sales floor to cashier. Okay, these are examples of transportation. And the last symbol that we will be using in constructing a flow process chart, that would be the symbol capital letter D, which represents delay. And delay is used in situations like temporary waiting of something or somebody. What I mean about this is that it occurs when a part is not immediately permitted to be processed at the next workstation. Now, examples of delay, that would be the time spent waiting for maintenance and repair activities, okay, because the operator will be brought into idle time if that happens, especially if there is machine breakdown or bug down. And also the time the customer spent waiting in a queue, okay? And as you can see in figure 2.8, the ASME standard set of process chart symbols. So these are additional examples of symbols used in constructing the flow process chart. So in operation, it can be considered an operation if the operator is driving a nail, mixing, or drilling a hole. For transportation, we have moving material by truck, moving material by conveyor, and moving material by carrying or through messenger. And for storage, we have raw material in bulk storage, finished stock stacked on pallets, and we also have protective filing on documents. And for delay, we have waiting for elevator, or operator is waiting for elevator. We also have material in truck or on floor at bench waiting to be processed by the operator. And also we have papers waiting to be filed. And lastly, we have inspection. And for inspection, we have examine material for quality or quantity. So you are inspecting in that case. You also have reading steam gauge on boiler. Okay, that's also considered as inspection. And examine printed form for information. And take note that there are 3 common types of flow process charts, okay? This is based on what is being charted by the analyst. First, we have the man type process chart. Second, we have the material type process flow chart. And lastly, we have equipment type or material type process flow chart. Now, if we say man type process flowchart, it shows the process from the point of view of the operator, which indicates the activities of the operator throughout the process. So in simple terms, if we say man type process flowchart, if I am the analyst, the one that I am studying is the operator. So that is why it's called man type process flowchart, because I am observing all the movements of the operator, or what the operator is doing all throughout his or her process. And if we say material type process flowchart, it shows the process from the material's point of view utilized during the process. It shows the introduction of all materials, whether raw material or finished components, and represents all information regarding operation and inspections carried out on the duration process dramatically. Okay, so in simple terms, if we say material type, it's not the operator that you are studying. Instead, it's the material that the operator is using or manufacturing. Okay, it's the material that you are observing all throughout the process. And if we say equipment type, it shows the activities from the viewpoint of the machine or equipment involved. So meaning to say, the one under study here is the machineries and equipment. All right. So in order for us to better understand what a process flow chart or flow process chart rather, and how it looks like, this is an example of a flow process chart. So as you can see in figure 2.10, flow process chart or material for preparation of direct mail advertising. Again, this type of process chart is material type, meaning to say the analyst is observing the material, not the operator, not the machine, but the material all throughout the process. Okay, so as you can see there in the sample given, you have there the location. So in this case, the location is Durban Ad Agency. Again, this is the preparation of direct mail advertising. So the location where the analyst is studying this is in Durban Ad Agency, and the activity preparing direct mail ads. And the date is January 26, 1998. So operator's name, only the initials that is acceptable. So you have JS, okay? And the analyst is AF. Operator meaning the person that is handling the material that you are studying. And also you have the analyst, or you being the observer or the analyst of that certain study. Now you have there circle appropriate method and type. Now in a flow process chart, there are two methods involved. First is the present method, and second is the proposed method. Now in this case, since this is your very first study on this particular activity, then you will encircle present, okay? This is your present method. It can only be a proposed method if from your present method, you have identified a lot of problems and in which there are also related improvements. So you, in that case, you will encircle proposed, but here in our example, since this is our very first study on this particular activity, then we will encircle present. And the type of chart is material type. Again, we are studying the material all throughout the process. Now, as you can see on the right portion, the right upper part of the chart, you have there the summary. And summary is divided into 4 columns. You have there the event, the present method, the proposed method, and the savings. Okay, so in event, you have their descriptions of the events. You have their operation, transportation, delay, inspection, storage. And you also have there the total time taken. You have there the total distance expressed in terms of feet. Okay, now in the bottom part of the chart, you have there the event description. The event description should be in chronological sequence from the very first process down to the very last. So in this case, you have there stock room. Okay, and beside the event description, you have their symbols, right? So remember, there are 5 symbols that we will be applying if we construct a flow process chart. So in this case, you can see their circle, transportation or arrow, capital letter D for delay. You have their square for inspection, and you have their inverted triangle for storage. Now, since our first event description is stockroom, meaning to say the material under study is being stored. So that is why you highlighted the triangle, the inverted triangle, because it is being stored. Okay, the material is being stored. Another, to collating room, meaning from stock room to collating room. So you transferred that material from stock room to collating room. Okay, so that is why you highlighted arrow. Okay, arrow going to the right. And since there is a distance traveled, okay, the operator traveled a certain distance from the stock room to collating room, then you need to get the distance. Okay, you need to measure. So in this case, the distance traveled by the operator is 100 feet. Okay, next is collating rack by type. Now, if we see collating rack by type, the material is being delayed. Okay, so that is why you highlighted capital letter D. Next, collate 4 sheets, meaning to say the operator or the material rather, meaning to say the material is being processed by the operator. Okay, so that is why you encircled a circle. Okay, so and so on and so forth. So anything that has distances traveled, you need to measure that one. So in this case, after you have identified all the symbols from each event description, then you need to go to the summary part. Now, since this is a present method, you need to get the total time for each event. Now, for operation, how many operations do we have? So we have collate 4 sheets, we have jog, fold, and crease. We also have staple, and we also have addressing. So a total of 4 minutes. Although we cannot really tell that it's 4 minutes because in this example, in this particular example, the time was left blank. There was really no numeric values being indicated. So let's just assume that for each of these operation, that would serve 1 minute. So a total of 4 minutes, okay? For transportation, you also have there a total of 4, right? Transportation symbol is arrow. So you have there to collating room, to folding room, to angle stapler, to mail room. So again, assuming that each process serves 1 minute, okay? So for transportation, you have 4 in the present method. And for delay, you also have 4 minutes. For inspection, there's none. So that is why it's 0. And for storage, you have 2. So that is why it's 2 minutes. And for distance traveled, so you have there 100 plus 20 plus 20 plus 200. So a total of 340. Okay, so that is an example of how to construct a flow process chart. And next up, we have another example of a flow process chart. And in this case, it's already the worker that we are studying, right? So it's the worker that we are studying this time. Now, as you can notice, you have their event description, you have their symbols, and as you can notice in the time, it's already entered, it's already identified, so you can already see the time taken by the operator in doing such process, and you also have their distances traveled. And for methods recommendation, this is the portion or the section in which you can specify your recommendation. So these recommendations are your recommendations for improvements. So you will be using these recommendations once you do your proposal, okay? So let's say, for example, for the first event description, leave vehicle, walk to front door, ring bell, okay? So that takes, that took the operator 1 minute to do this process, okay? And the distance traveled in feet, that is 75 feet. Now, the recommendation of the analyst says, call home in advance to reduce waiting delay. Okay, so you will be using this in your proposed method, and so on and so forth. And like the operation process chart, the flow process chart is identified by, we have a title. So in this case, that would be flow process chart. We also have accompanying information that usually includes the following. First, we have the part number, drawing number, the process description, the present or proposed method, the date as to when the study was conducted, the name of the person doing the charting or the analyst, and also additional data that may be valuable for completely identifying the job being charted include the plant, building, or department, the chart number, the quantity, and the cost as well. All right. So how does a flow process chart work then? Well, the typical approach is to chart the present method first, then the improvement will be proposed on a second chart. Now, when charting for the future, each process activity is subject to elimination, combination, and sequence changing. Again, that would be elimination, combination, and sequence changing. And take note as well that improvements can also be achieved by reducing the number of activities, reducing the time each activity takes, or reducing the distance of travel for the transport activities. All these improvements on the process will help in the cost reduction effort and justify any improvement for proposal. We will be using, aside from a flow process chart and operation process chart, that would be flow diagram. Although the flow process chart gives most of the pertinent information related to a manufacturing process, it does not show a pictorial plan of the flow of work, correct? Sometimes this information is very helpful in developing a new method. For example, before a transportation can be shortened, the analyst needs to see or visualize where room can be made to add a facility so that the transportation distance can be shortened. And likewise, it is also helpful to visualize potential temporary and permanent storage areas, inspection stations, and work points. Now, the best way to provide this information is to take an existing drawing of the plant areas involved and then sketch in the flow lines indicating the movement of the material from one activity to the next. Now, as you can see, if we see flow diagram, it is a pictorial representation of the layout of floors and buildings showing the locations of all activities on the flow process chart. Now, when constructing a flow diagram, analysts identify each activity by symbols and numbers corresponding to those appearing on the flow process chart. Now, the direction of flow is indicated by placing small arrows periodically along the flow lines, and different colors can be used to indicate flow lines for more than one part. Now, as you can see in figure 2.12, this is an example of the flow diagram of the old layout of a group of operations on the Grand Rifle. Figure 2.12 illustrates a flow diagram made in conjunction with a flow process chart to improve the production of a Garand M1 rifle at Springfield Armory. Now, this pictorial representation, together with the flow process chart, resulted in savings that increased production from 500 rifle barriers per shift to 3,600 with the same number of employees. Again, as you can notice, that's a very good savings, right? Now, another, as you can see on figure 2.13, it illustrates the flow diagram of the revised layout. The flow diagram is a helpful supplement to the flow process chart because it indicates backtracking and possible traffic congestion areas, and it facilitates developing an ideal plant layout. And the next tool that we can use or we can apply or employ in our study, that would be worker and machine process chart. Now, if we say worker and machine process chart, it is used to study or analyze and improve one workstation at a time. Now, the chart shows the exact time relationship between the working cycle of the person and the operating cycle of the machine. Now, these facts can lead to a fuller utilization of both worker and machine time and a better balance of the work cycle. And also, we should always remember that many machine tools are either completely automatic or the automatic screw machine or semi-automatic or the turret lathe. With these types of facilities, the operator is often idle for a portion of the cycle. The utilization of this idle time can increase operator earnings and improve production efficiency, correct? That is why if there is idleness in a certain production area, or if the operators are brought into halt due to, let's say, machine breakdown or backdown, we can actually try to improve that. An opportunity for improvement. Okay, so we can have a significant savings to that. And so for that matter, what usually happens is that when an operator is idle in a certain machine that he or she is operating, then in order to somehow eliminate that idle time and transform it to a productive time to improve the operator's productivity and production efficiency, then the operator may be assigned to an additional machine. And if we do that, that's what we call machine coupling, or the practice of having one employee operate more than one machine. But the question is, do you think adding more work or additional job to the operators make them happy? Well, in reality, of course not, right? In fact, it can be demotivating for them. So as methods engineers or industrial engineers in general, how do we go about it? Well, like I said earlier, organized labor may resist this concept, the concept of adding them additional workloads, but the best way to sell machine coupling is to demonstrate the opportunity for added earnings. Since machine coupling increases the percentage of effort time during the operating cycle, greater incentive earnings are possible if a company is on an incentive wage payment plan. And also, higher base rates result when machine coupling is practiced, since the operator has greater responsibility and can exercise greater mental and physical effort as well. Now, when constructing the worker and machine process chart, the analyst must find or must first identify the chart with a title such as worker and machine process chart, and additional identifying information would be the part number, the drawing number, the operation description, the present or proposed method, the date as to when the study was conducted, and of course, the name of the analyst as well. Now, since workers and machine charts are always drawn to scale, the analyst selects a distance in inches to conform with a unit of time such that the chart can be neatly arranged. And the longer the cycle time of the operation being charted, the shorter the distance per decimal minute of time. Once exact values have been established for the distance in inches per unit of time, the chart is begun. And the left side shows the operation and time for the worker, and the right side shows the working time and idle time of that time. Now, a break in the vertical work time line signifies idle time, and likewise, a solid vertical line under each machine heading indicates machine operating time, and a break in the vertical machine line designates idle machine time. A dotted line under the machine column indicates loading and unloading machine time, during which the machine is neither idle nor productive, as shown in figure 2.14. Now, as you can see in figure 2.14, it shows that the analyst charts all elements of occupied and idle time for both the worker and the machine through the termination of the cycle. Now, at the bottom of the chart, it shows the employee's total working time and total idle time as well as the total working time and idle time of each machine. Now, the productive time plus the idle time of the worker must equal to the productive time plus the idle time of each machine that the worker operates, okay? Now, accurate elemental time values are necessary before the worker and machine chart can be constructed. And these time values should represent standard times that include an acceptable allowance for fatigue, unavoidable delays, and personal delays as well. The analyst should never use overall stopwatch readings in the construction of the chart. And also, as you can notice, the completed worker and machine process chart clearly shows the areas in which both idle machine time and idle worker time occur. Now, these areas are generally a good place to start in effecting improvements. However, the analyst must also compare the cost of the idle machine with that of the idle worker. It is only when total cost is considered that the analyst can safely recommend one method over another. And the last chart that we can employ, that would be what we call Gantt process chart. So Gantt process chart is, in a sense, an adaptation of the worker and machine chart. Why is that so? Because a worker and machine process chart helps determine the most economical number of machines one worker can operate. However, several processes and facilities are of such magnitude that instead of one worker operating several machines, several workers are needed to operate one machine effectively. And also, it shows the exact relationship between the idle and operating cycles of the machine and the idle and operating times per cycle of the workers who service that machine. Now, this chart reveals the possibilities for improvement by reducing both idle operator time and idle machine time. Now, as you can see in figure 2.15, it illustrates a Gantt process chart for a process in which a large number of idle work hour exists, up to 18.4 hours per 8-hour shift. Okay, as you can see, this chart also shows that the company is employing 2 more operators than are needed. By relocating some of the controls of the process, the company was able to reassign the elements of work so that 4 rather than 6 workers could effectively operate the extrusion press. Now, as you can see in figure 2.16, it is a better operation of the same process is shown on the Gantt process chart in figure 2.16. Now, as you can see on the proposed, previously that was the present method, and this is now the proposed method. And as you can see, the savings of 16 hours per shift was easily developed through the use of this chart. All right, I think that's a good place to stop. If you like this video, please don't forget to subscribe and hit the bell button for the latest updates. Thank you.